PID controller, proportional integral derivative controller, produces feedback to reduce measured error in the next step. So PID controller is a tool that we can use in case of a measured value, which is called process variable for time series, where ideal value is known, and we can provide feedback in the next step. We can provide feedback to correct. So I do lots of videos like this on machine learning and software. You can subscribe on my website welsofcourser.com, or you can subscribe on YouTube as well. Ask me questions if I make mistakes. Please let me know. I would be interested to learn more. I'm sort of on this journey of becoming more knowledgeable in machine learning in general, and then one day I will start applying it for some kind of specialized use case. Right. So what we are doing now. So when to use PID controller. As I mentioned, you have this process variable, which is time series, you have the ideal point, set point, and you can provide feedback to sort of throttle the correct to get closer in the future steps to your ideal value. So what kind of tuning do we need? So there are three parameters, three coefficients that we need to tune based on training data. I will describe that shortly, but some training data is required. And we usually use these PID control when we cannot model or predict the process, when we have no other mechanisms to predict from the past values the future. In non-linear systems, the PID control may not work. Example use case is cruise control. So the process variable there is the speed. The set point is ideal speed that we configured. An error is the ideal speed minus actual speed, and the feedback is a gas on the pedal. Gas pedal pressure, basically. What is PID controller actually? So it's sometimes called free-term controller. It's a tool to stay close to the ideal state. They are control loop mechanism. So basically, control loop mechanism is this idea that from previous steps you can apply what you've learned to the next steps to stay in control of the process. It uses the PID controller uses distance from set point, this error, to produce feedback, which is then used as described as a learning. It is defined as a sum of three terms. First one is a proportional term, which is proportional to the current error. It corrects for error in the previous. Well, it's basically proportional to the error, and what it basically is proportional to the previous error in the previous step. So it the bigger in certain direction it was, then it tries to correct for that in the next step. The integral term is the sum of previous errors till now, and so more consistently the error was in one direction in the past, the more it corrects in the opposite direction. That's the meaning of the integral term. The derivative is proportional to the current or basically previous step derivative of the error, and this one can cause instability. It's not used very often. If it's used, there is low pass filtering, so we prevent huge jumps, huge derivative values. And what this one does is basically for if there is a quick change in error, we do bigger correction once again. So the proportional term, so the bigger error there was in the previous step, in that direction we do opposite direction we do the correction correspondingly. Integral term, the bigger the error was in general in the past in certain direction, proportionally we correct in opposite direction. In derivative error is that the bigger there was a change in the error recently, the bigger we correct as well. So in mathematical terms, you can look at this description, right? It's the sum of these k times the error, that's the proportional term, ki times the integral from 0 to current of the error over time. plus kd times a derivative, which is proportional to the change of the error in the previous step. We can as well look at the demonstration where the gray dots represent the set point, right? So the gray dots here are around the zero values or some kind of set point, while the blue represent the original measured values, which we want to correct, which we want to push towards the set point. And the red represents the process variables after corrective feedback was applied. The process is effective in this case. It's very simple. It's just process variable minus feedback, and minus basically the corrective feedback, and the errors obviously are how after applying this how big the error was. So we can see that in case of the step function where the blue value changes from here to here, basically from 0 to from plus something to minus something, you can see that after the change for a while we converge to the set point, and then we stay on the set point until next jump. In case of a sine function, the red shows us that we dampen, we suppress the movement of the blue function, but of course we are not exactly at 0. There are possible extensions. For example, as I mentioned, these free proportional parameters, these big K's needs to be tuned on training data, but there is a variant of a PID controller which uses Kalman filter to actually learn those, tune those as we go. And it's basically Kalman filter uses linear relationship between the measured values to estimate true values and uncertainty. And how they use it in that paper is that they actually derive that the PID parameters between each others have a certain relationship. And this relationship is then used for definition of the Kalman filter, and then the Kalman filter is used to tune those values. The Kalman filter tunes this Kp, this Ki, and this Kd. Alright, there is also a related post that I did in the past about Kalman filter, which you can use to understand Kalman filter better. It deals with the degenerate case, the simplified case of the Kalman filter in one dimension with a special other case. Well, so let's look at it. In one dimension with constant measurement uncertainty and process noise, the filter converges to either a cumulative average in case of a zero process noise or exponential average in case of non-zero process noise. So the Kalman filter in this case still very useful, but actually it's just what you would expect, these sort of two most simple ways to estimate those values. In one dimension, basically the Kalman filter doesn't make much sense, but you can use it to understand partially how it works. Alright, so that's all about the PID controller. Just a quick video. Hope to see you next time. Let me know if I made any mistakes, or as well if you have some interesting papers you would like. Do you think it would be useful for me to look at? I can look